We're going to be looking at applications of the definite integral as they apply to some of our word problems we're going to see in AP Calculus. Now, if this is the first time you're seeing my face, hi, my name is Dr. Marissa May, and I'm on a mission to help students feel confident in their math class. So, today we're looking at AP Calculus. This is an AB or a BC topic, so I encourage you to take a look and let's see how we can do with some explanations here. So remember that anytime we take the derivative, we are finding a rate, right? And so when we take, let's say we have water being drained from a swimming pool. If R represents the amount of water, and we take in cubic feet, and we take the derivative of that, then R prime actually means the rate the amount of water is changing. Meaning if that rate is positive, then the water amount is increasing, right? If that rate is negative, then that water amount is decreasing. Now, if we take the integral of that rate, we get the amount of change. So if we look at an integral like this, we have find the integral from a to b of the rate, right? We get the change in the amount of water. For this problem, this is the change in the amount of water in the pool from t equals A to t equals B. Okay, let's see if we can use that. We are being given the velocity of a particle. We're giving it in a table. We're asked to approximate this integral using a midpoint Riemann sum and then explain what it means. Okay, we know from some of our previous work that when we take the integral of the velocity, that's the net distance. So let's go ahead and explain what it is. This is the net distance traveled from t equals 0 to t equals 30. Okay, now let's do the midpoint sum to approximate. So if we're going to do a midpoint, we're going to have to break up the intervals like this. Okay, so that first interval, we'll just do this and do an approximate. The width is 10, and we get our height in the middle, which would be 1.6. The width is 10 of the second one, and we get our height in the middle, which would be 3.1. And the final one, the width is 10, and we get our height in the middle, which would be 1.6. So it looks like we get 16, 31, and 16, which would give us 63. And the units are in feet because this is total distance. Okay. So B asks us what is the value of 5 to 25 of A of t and explain what this means. So remember, if I'm going to take the integral of the acceleration, I'm getting the change in the velocity. This is the change in velocity from t equals 5 to t equals 25. Okay, so let's see if we can calculate that. So we want the integral from 5 to 25 of the acceleration. The antiderivative of the acceleration is the velocity, and we're going from 5 to 25. So plug in our 25 minus plug in our 5. Velocity at 25 is 1.6. Velocity at 5 is also 1.6, so we get 0 feet per minute squared. Okay, so remember, it's all about interpreting what we are finding. So let's take a look at this scenario. The temperature of water in a tub is modeled by a strictly increasing, twice differentiable function W, where W is measured in degrees Fahrenheit, and you have table. So using the data in the table, estimate W prime and interpret its meaning. So let's do W prime of 12, and we'll have to use the slope the algebra way. So let's do W at 15 minus W at 9, and then we'll subtract 15 minus 9. Now, W at 15 gives me 67.9, and W at 9 gives me 61.8, and this is over 6. So if I subtract on top, I'm going to get 6.1 over 6, which is going to be 1 point something. Whipping out calculator here. Oh, not pretty. 1.017, and that's in degrees Fahrenheit per minute. So what does this mean? The temperature is increasing at T equals 12 degrees, or sorry, 12 minutes. Okay, let's look then at now the second part. Use the data in the table to evaluate this integral. So, and then interpret its meaning. So if we're doing the integral of the rate, we're going to get, this is the amount of change in the temperature from T equals 0 to T equals 20. Okay, now let's calculate it. We're doing the integral of W prime. So that antiderivative is going to be W. We can plug in our bounds now, W of 20 minus W of 0, and get our value from the table. W of 20 is 71. W of 0 is 55. And we get 16 degrees Fahrenheit. All right, last one here. For the interval 20 to 25, the function that models the water temperature has a first derivative given by this function. Based on this model, what is the temperature of the water at time t equals W? All right, so let's go ahead. We're going to use fundamental theorem here. So we're going to do an integral from 20 to 25 of W prime. And we know that we should get W from 20 to 25. Okay, now let's go to our calculator to find out this integral. I'm going to share with you how I can put this in my Desmos graphing calculator. If you want to use the integral, you can add an item here and it will let you put in an expression. I did it by just typing int for integral, and Desmos was able to give me the value that I needed there for this side of the integral. Whoops. And so that gives me 2.043. Now I'm going to plug in my bounds for the other part, W of 25 minus W of 20. And let me switch my view back so you can see a little bit clearer. Now, W of 20, I know from the chart is 71. So I'm going to plug that in. And then I'm going to add the 71 to the other side. I'll get 73.043 is what W of 25. And this is degrees Fahrenheit. So I hope that helps for today with kind of understanding the applications of the integral, knowing the difference between the rate and the amount of change. If there's something you'd like to see a video of, don't forget to leave me a comment. I'd love the opportunity to help. But thanks for watching. Bye for now.